All right, so let's just review real quick the lab yesterday. The lab yesterday we had the first graph looks something like this, and another piece looks something like that. Correct? All right, is this where equilibrium is? No. This is where equilibrium is. Correct? All right, this was height, but it could be concentration for us in real life versus time. You have to be able to recognize this graph as a graph of equilibrium. You have to be able to indicate where equilibrium is reached. Sometimes that's a number, and if it's a number, they've just graduated the x-axis. You would say, hey, it was reached by about day whatever, and it's a very simple question. Okay? Now, it reaches equilibrium because the rate forward equals the rate reverse. Once that rate is equal, then both sides will stay the same forever. Pretty simple concept. Is that okay? Today we're going to throw math on top of it because that's what we do in chemistry. The math isn't bad. The math, we are just going to have a ratio. So we're going to divide pretty much the concentration of my reactants and my products. It really isn't that bad in the grand scheme of things of what we've done. So the concept of equilibrium, which we already talked about before I left, was that it occurs when a reaction and its reverse reaction proceed at the same rate. Okay, pretty simple. We're creating as much as we're destroying, so there really is no change. All right. As a system approaches equilibrium, both the forward and reverse reactions are occurring. At equilibrium, the forward and reverse reactions are proceeding at the same rate. All right. Said that like 3 times. So this is showing you the rate. Initially, when we learned it in chapter, our rate is pretty fast. But the rate slows down because the amount of reactants starts to decrease. The less concentration, the slower the rate. All right? And the rate that the products are being produced, it increases pretty fast until it eventually slows. All right? Because now there can't be products made as fast because the reactants aren't colliding as fast. Eventually the rates will be equal. Now notice, this is a graph of rate versus time. The concentration, the graph over here was concentration versus time. All right? So that's why over here they end up being the same line. But they did not at equilibrium. All right, so once equilibrium is achieved, the amount of each reactant and product remains constant. It doesn't mean they're equal to each other. It just means that they are constant. They are not changing. We okay with that? So in a system at equilibrium, both the forward and reverse reactions are being carried out. As a result, we write its equation with a double arrow. That's like the only difference that we've done all year. The arrow would point both directions. Sometimes, as you can see here, it's written as a half arrow on top and a half arrow on the bottom, or sometimes it's just a double-sided arrow. They mean the same thing. Does it say that? Maybe it doesn't. Going this direction, we call that the forward reaction. Going this direction, we call that the reverse reaction. That is 2 vocabulary words that you're expected to know and be able to use. Not that bad. So all year long we've been studying the forward reaction. Now we're just saying, hey, it could go both directions. And okay. All right, so here comes the math. And I promise the math is not awful. So we call it the equilibrium constant. All right? And it is signified as KEQ. K is the constant, which I know the word constant doesn't start with K, so don't ask. All right? EQ means at equilibrium. All right? Now, get rid of some of these things because we don't need that yet. It turns out that there are a lot of different ways that we can express this K value. All right? We have KEQ, and KEQ pretty much means all of these things. And we're going to learn all of them. These two are in this chapter, the top two. KSP, you can obviously read, is 17. KA is 16. KB is 16. KW probably is next, and that's chapter 16. The nice thing about all these Ks is, yes, they're for different things, but they're the same math. Okay, so chapters 15, 16, and 17 are really pretty much the same math over and over. Okay, so a lot of you are writing that down. I guess I'll just pause, but don't really don't overthink these. They're if you like chapter 14, chapter 15 and 16. Well, 16 is really hard, but you like most of chapter 16. It's KW or K water. This one we don't really talk about that much because this is always equal to the same number no matter what. But we use it in math. If you had chemistry last year, I never called it KW. Right. So here we go. So this is a lot of stuff. Do not write down it because it's like how we came up with this stuff. So just chill for a minute. So our forward reaction, we have this is KF N2O4. Okay? I'm going to blow through this. I always do. Is KR, that means the reaction or the reverse. This is a little subscript. Equals NO2 squared. Okay? That came from here. All right? If we relate the two of them, they're equal to that. Or we can rewrite it KF over KR equals NO2 squared over N2O4. Rewriting that, okay, that becomes that. Don't write anything down yet. All right, the ratio of the rate expression is a constant at that temperature, and the expression becomes that. All right, so this ratio means dividing, right? So we're going to do some division here, and we're going to call this KEQ. End up, I have no idea why this is a dotted line, but whatever. We end up with this overall expression. And it's just for this particular one, but it works just plenty good. So when we find this ratio of your rate of forward and reverse, we end up with this ratio. Or we end up with your concentration of your products every time divided by your reactants. This is really the only part you have to remember is which one goes on top and which one goes on bottom. Okay? The products will always go on the top. Okay, here we go a little bit farther. All right. So, to generalize this expression then, is that a question? Yeah. Yep, you just put them all in. We're going to get there right now. Okay, to generalize this expression, consider the reaction AA plus BB goes to CC plus DD. Now that is confusing, but I've written out. So this number, that'd be your coefficient. A would be the identity of your compound. All right, so coefficient, compound. The expression, the equilibrium expression for this reaction would be KEQ. Okay, that's our equilibrium expression, or another name for it is the mass action expression. It becomes CC, D raised to D, over A to A, B to B. Or you will notice it becomes your products over your reactants. Who's with me so far? Okay? And it's kind of nice because whatever the number, the coefficient is, that becomes my exponent. I don't have to do math to find out my exponent anymore. I don't have to put in my calculator. I don't have to do any charts. I find my exponent because it's just the coefficient from the reaction. Okay? So, if you want to write anything down, you can. It's fine. Well, let's do an example. If I had water, H2 plus O2 goes to H2O. I need to put a 2 here, right? a 2 here, and a 1 there. And then I could write the equilibrium expression for this. I would say K EQ equals H2O, and it's going to be squared because it's my product raised to its coefficient over my reactants raised to their coefficient. You don't have to put a 1, but I'll put a 1 just to kind of illustrate it. Are you okay with that so far? Okay, so your equilibrium expression will always be the concentration of your product raised to its coefficients, and if there's more than one, you just keep on going, divided by the concentration of your reactants raised to their respective coefficients. And if there's many of them, you just keep on going. Not bad so far, hopefully. Okay. Welcome, Isaac. All right. Anyone need more time on this slide? Okay. So here we go. For each of the following, balance the reaction and then write the mass action expression. For now, you can ignore the state of the species that they're in. That will matter eventually, but we don't really care. And some of these, because I just clipped this straight from a regular chemistry piece of paper, most of these wouldn't even really have one, but don't worry about it. So number 1, we can do it together. We would balance. All right, I see a 3 and a 2. Okay, so that would be that. So my KEQ for this expression, or this reaction, I should say, would be AL to the 4th. You okay with that? O2 to the 3rd, and Al2O3 to the 2nd. Okay? Will you just do a couple of those yourselves? You don't have to do all of them. If you still struggle with balancing, that's fine. Do your best. My watch tells me we're out of time. So I'm just going to do number 5 because it's the shortest one. So I would have my KEQ equals Ag2S over Ag squared and S to the 1st. Fair enough? Hopefully it's extremely easy. All right, now KEQ is most often, since I'm using these brackets, it would really be KC specifically because I'm talking concentration. All right? So it's kind of tricky vocabulary here. KEQ simply means the equilibrium expression, but there are different ones. C means if I list it as concentrations, which that does. P, that will mean pressure. If they're all gases, we'll talk pressures. If it's A, we're talking about an acid. If it's B, we're talking about the concentration of bases. If it's W, we're talking about water. If it's KSP, we're talking about the concentration or the solubility product of things when they dissolve. So it's tricky. Just make sure you know which one we're talking about. But most of the time, especially in chapter 15, we're dealing with KC, which is a KEQ, and then 10% of the time we'll talk about KP. Yeah, go ahead. Well, you don't ever use KEQ. It's just like the umbrella that all of them are. It's just saying all of these are the equilibrium expressions. Now, which way would you use them? All right, are we okay? Not awful. Let me see what the next slide is. Okay, so this one, I should not have written hard, really hard, but oh well, I did. So here we go. This slide kind of sums it up. KEQ is the general name for every single one of these. KC means it's concentration, and we use that in solutions. KP is pressures, and we use that when we're talking gases. KC and KP are related to each other, by the way, through math. We'll learn that. Ka, once again, acid. Kb, base, and these are some of the hardest things of the year. Kw is water. KSP, solubility product, And that, I'm not joking, that is one of the easiest things we do all year. So we're going to sandwich the hard stuff in the middle. But it's like an Oreo. Everyone likes the middle the best, right? We'll like the hard stuff best. Don't look at me that way. All right. So here we go. Because pressure is proportional to concentration for gases in a closed system, the equilibrium expression can also be Kp equals the pressure of C raised to exponent raised to its, the pressure of D raised to its coefficient, pressure of A raised to its coefficient, and the pressure of B raised to its coefficient. Now, here's the subtle difference, and yes, I know this is stupid. Kp, usually your numbers are in parentheses. Kc, your numbers are in what? Brackets. Why does it matter? It doesn't do math the same way. But like when you read it in a book, if it gives you brackets, then you're supposed to know brackets in chemistry mean concentration. All right? Parentheses don't mean pressure, but it's just mathematically how they write it out. So I'm not going to grade it. I don't care what you draw it in. But if you like see a problem in the book and it's parentheses instead of brackets, it's Kp versus Kc. All right, so here we go. We don't just want to write what it is, we want to figure it out. So this is the exact same expression we did before. So now we'll actually solve for Kc. So Kc, the general expression, would be Ag2 S, over, oh, I gotta stop talking, Ag2 S to the 1, right? So that's called the expression, or Keq, or Kc, or the mass action expression. All right, but doing the math, we just plug in the pieces. So I should go out, I guess, whatever. So the concentration of Ag2S is 0.2. All right, the concentration of this one, and I'm putting in parentheses, I guess, because I'm lazy. This is 0.2 squared, right? And this is 0.0, or they're all 0.0, sorry. 0.01 to the first. And then you just plug it in. Is this 61? Anyone do it yet? Nope. Okay. One of these today is 61. 5,000? Okay, sounds good. All right. We will use calculators the rest of the hour if you want to borrow one. I put them back here, I guess, for no reason. Oh, they're definitely sliding. All right. This isn't awful, is it? Comparatively, thank you, it's not. All right, you just have to write the expression, substitute the numbers in, and make sure you do your order of operations correctly. Okay? Make sure you always put the whole denominator in a parenthesis. All right? Or you can get the wrong number. All right, you want to do another one of those? You feel fine? Okay, another one of those. So you have water decompose to H2 plus O2, and we can balance that. There's got to be a 2 here, a 2 here, and a 1 here. At equilibrium, let's say this is 0.28, this is 0.15, and this is 0.09. Who knows? Okay, will you find Keq or Kc? All right. Oh yeah, it definitely can be decimals. K is weird. It can be extremely large and it can be super, super small. And we'll learn what that tells us, by the way. In fact, I might as well after this. But yeah, don't panic if it's a tiny number or a big number. Or a normal number. Like, it can be whatever it wants. All right. When I looked at calculators, 0.02 something, is that what it was? 0.026. Okay. Does everyone have that number on their calculators? Okay, that's an underwhelming answer, but whatever. All right. So we will learn this, but this is a small value, right? So a small value in a fraction comes when you have something big and something small. Correct? Are you okay with that? Let's substitute what is on top. These are your reactants. Are you okay with that? So, as written, we would say that this reaction is reactant favored. It favors the reactants. If K is a really small number, it means at equilibrium you have a lot of reactants and a little bit of product. Does that jive? Let's go to the previous one because it was a huge number, right? In fraction land, in order to get a big number, you need something big on top and something small on the bottom, right? So that would mean we have a large amount of products and a small amount of reactants. So we would say this reaction, as written, would be product favored. Meaning at equilibrium you'd have more products than you would reactants. We'll go over that again later, but that's what it means if you have a big or a small number. The closer it is just to 1, the less either side is favored. Okay. I put this slide on here because years ago, kids came back from the AP test and they were like, what in the world is the mass action expression? You never talked about that. And I was like, I didn't. We spent a month on the mass action expression. But I just hadn't used that in my vocabulary, and so I don't know if they all failed or not. Mass action expression is just this exact same thing. It's when we write the products over the reaction. So if it says, give me KEQ or KC or KP or give me the mass expression for the following reaction, it all is the same thing. Okay? I've regretted that because that may literally have cost some kids because they knew what to do. They just didn't know the right vocabulary. All right. Do you want to do one more or should we move to the next piece? Move on. Okay, good idea. All right. So here we go. I did not like a lot of stuff when I was your age in chemistry, but I liked these. And I still do. I don't know why. I think it's because they were like 1% harder than most things, but I could do them right. And I needed some your age in chemistry. All right. I introduced one of these last chapter. We'll just kind of go through it together. A useful tool in solving equilibrium problems is an ice table. Because, unfortunately, you don't always have a problem where it just gives you the 3 equilibrium concentrations and you just plug it in. Most of the time you don't. You're given a handful and you got to figure out everything based on that. So, in an ice table, I stands for the initial concentration or pressures for each species in the reaction. All right, C represents the change in the concentration or pressures for each species as the system moves towards equilibrium. E represents the equilibrium concentration or pressure of each species when the system is in a state of equilibrium. All right, for this part, E is what I really care about because that's what I'm going to shove into my mass action. You okay with that? So E is what we're looking for. So it says, a sample consisting of 0.5 mole of X is placed into a system with a volume of 0.75 liters. For right now, talk about that tomorrow. So let's just pretend this is concentration. Okay? All right. At equilibrium, the amount of the sample is known to be 0.350, and we'll once again say capital M. All right. So I have this ice table. It told me right here that X started at 0.5. It tells me that X ends at 0.35. Every other spot where there's a question mark, I can figure out based on that. And we'll do a few of these, so just each one of you will pick it up at a little different rate. Just be patient. So the change is simply the difference. All right? The difference is negative 0.150. Okay? This decreased 0.15. Are we okay with that part? All right? Now, we're going to apply stoichiometry to this. What does stoichiometry mean we're going to use? Coefficients. Well, the picket fence too, but we won't use the picket fence ever. The picket fence, we used the balanced coefficients in it. That's the stoichiometry. All right, we're going to use the coefficients to tell me what the other changes are. Now, this number will be pretty easy. And for some of you, that one might be also. But let's do that one first. So here we go. This is 2. That's a 4. So Z changes twice as much as X. Are you okay with that? Changes twice as much as of X. So my change will be 2 times the value of X's change. Because from 4 to 2, that's twice as much. So the change here is a positive, and I'll tell you why in a second, 0.3. All right. The reason why it's positive is because reactants go down over time, and products do what over time? They go up. Are we okay with that? Okay. Now, if you're fine at math, you may already know this number. But I'm going to teach you how I did it when I was your age. Because I wasn't super good at 2/3 or 3/2. All right. So this one is to 2 ratio. This is how I did it when I was your age. And if you don't need to do this, you don't need to do this. Since this was a 2, I just divided this number in half. And it was 0.075. Okay? And I'm not writing that in my ice table. I'm just writing it above my ice table. Because now, it would be 0.075 if this was a 1, correct? So now I just take this number and I multiply it by 3. And that will tell me what that number is. That's a positive. Did that make sense? It's the same thing as multiplying it by 3 and dividing by 2, but I struggled with that when I was your age. So I would just always convert it to what it would be if it was a 1 and distribute that all the way through. Okay. Now, we're actually super ready to go. I now take my change, and it's 0.225, my initial, and add my change, and it's 0.3. And now I have the concentrations at equilibrium right here. And I'm ready to roll. Okay? I had y to the 3rd, right here, z to the 4th, that's right here, divided by x to the 2nd. And then I just plug them in. 0.225 cubed, 0.3 to the 4th, and x was 0.35 squared. And I would just plug those in and get a super awesome number. Maybe a rock had asleep that way. Just most halfway in the splits. All right, did we get an answer? What's that? Yeah, it's out there. I never thought in my life that sleeping this way would be comfortable. I can't even do it. All right, what did we end up with? Anyone have that? -4? Did anyone else get that number? Okay, then it's right. Make sure you type them in correctly because there's a lot of ways to screw up math here. When in doubt, parenthesize. Okay, based on a short conversation we had a couple minutes ago, tell your lab partner whether you think this is reactant or product dominant or favored. All right. Not the worst thing, hopefully. We got more of them. This is something you do need to get really, really good at. Okay. For the reaction, H2 plus I2 goes to 2HI. Initial concentration of hydrogen and iodine were both 0.4 molar. By the way, these are always going to give you the temperature. You never need to worry about it. It's there because these only exist at specific temperatures, but they're not things we're going to use. All right, the concentration of hydrogen iodide, which is the HI, was 0.13. Determine the concentrations of hydrogen and iodine at equilibrium and determine the equilibrium constant for the reaction. So I'll just set up an ice table. Okay. So I have H2, whoops, I need to write that above. H2, I2, and 2HI. Good so far? I plug in the initials that it gave me. It said that both of these were 0.4. And then if it does not say anything, then you assume you had 0 of the other. Okay? What's that? Did I do something wrong? Okay. So now, at equilibrium, so in the E row, it tells me that this is now 0.13. How about you take 2 minutes and try and do the rest yourselves? All right, so my change here would be a negative 0.13. Thank you. Which would make both of these a negative, correct? All right, so if we look, this is twice as much change as the other ones would be, correct? So this would be 0.065. We okay with that? So coming down here, we have 0.335. And those are our equilibrium concentrations. Okay, let's lower down here. So now I have HI squared and then H2 to the first, I2 to the first, and we're ready to roll. So 0.13 squared. And these are the same. Would you care if I just put 0.335 squared? Because it's just, that's what it is. All right? And then most of you probably have this as I looked in your calculators, but you don't all have the same answer. So the most common one I saw was 0.15, I believe. Will you all double check that you get 0.15 when you type that into your calculators? Maybe the 0.3s didn't divide in half or something, because I did see 0.3 something a few times as well. Okay? Not because they go down. The concentration of your reactants will go down in a reaction, and then these are created. Taking away from the reactants to make the products. Okay, raise your hands if you're okay so far. All right. Okay, here's another practice. Give this one a shot. Oh, I can pause that. So your change here is positive 0.4, right? That would mean the change here is what? 0.2. All right. The way I would do this is I would divide this in half, which I did here, correct? And then just multiply it by 3. Negative 0.6. Does that make sense? Okay. If you ever can get 1 to a 1, it makes all the rest of them a lot easier. All right, so this is 0.2. This is 0.2. And then you just plug in and get 100. Okay. Give me 5 fingers if you... Okay, so this is just like the one from the test. All right. This is the one from the test. Not the one, but it's like it. Try those 2 parts, and we'll learn the rest of these 2 parts tomorrow.